6 today, and it was only about 6 2006. So, you know, it has grown by quite a lot from 6 in 2006 to 106 today. You can see that it's almost a 20-fold increase. And well, this is why the topic is quite relevant. And also, you know, the Nobel laureate economics World Prize was given to yesterday, well, the day before yesterday, to two guys, two experts, two professors on economics, which have dedicated their academic life to auctions. So I think it's, you know, quite a timely topic today, not only because, you know, how to promote renewable energy, but also because auctions themselves. Okay, so we're going to see today, I try to go quite fast on this, and I hope to cover all the 6 points. I'm not sure I will do with the last one, but you have a lot of information, a lot of references that you can use after the training, but I will try to cover it anyway. Well, I start to, you know, to give a brief introduction on what are the options to promote electricity, including auctions. I will describe and try to define how auctions work. I will also look at some analysis undertaken on auctions. I will show you the importance of auction design and how can auctions be designed. There are many design elements that we can choose from, and so I think this is also very important. The success of auctions depends on how they are designed. So this is quite an extremely important point. And therefore, the pros and cons, the drawbacks and advantages of different design elements is a very important topic, of course. So, you know, we're in an energy transition everywhere, and we need to decarbonize our electricity and energy systems. And this means that we will need substantial increases in renewable energy everywhere. You can see this from IRENA. IRENA is the International Renewable Energy Agency. And a lot of the documents that I will use throughout this presentation are from the IRENA. So you are invited to visit their website. It's a lot of interesting documentation, a very relevant one. So you can see that annual PV additions and wind additions will need to increase strongly in the next 10, 20, and even 30 years, you know, in order to achieve this. By the way, I will focus this presentation on electricity. Renewable energy can be applied in different sectors. It can be applied in transport. You got some type of insight yesterday on this. You can also apply renewable energy for heating and cooling. And you can also apply renewable energy in electricity. The focus of this topic will be on electricity. Okay. So, what are the options to support renewable energy? Well, first of all, why should we support renewable energy? Well, renewable energy brings a lot of social benefits. It reduces CO2 emissions, and therefore they provide a social benefit. But the problem is, at least up to now, and this will no longer be the case in the next 5 years, but up to now, they have had the private cost of generating electricity with renewables has been above those of conventional sources. This is no longer true in many parts of the world. This is no longer true for some technologies in some parts of the world, but, you know, more or less it can be said that it is like that. Okay, so we can either set a remuneration for this renewable energy, for the generation coming from renewable energy projects. This means that renewable energy projects produce electricity, and this electricity goes to the grid. And the renewable energy generators would be paid in addition, you know, and they can be paid a total amount, what we could call a feed-in tariff in euros per megawatt hour. They can be paid a premium. This means an additional amount to the price of electricity that they get when they sell electricity into the grid. This is the feed-in premium, fixed feed-in premium, or they can be paid the difference between set feed-in premium and the price of electricity, such as in a sliding feed-in premium. In a sliding feed-in premium, what you see below in the last part of the graph, when the electricity price is above a reference price, also called the strike price, the electricity generator receives the electricity price but has to give back the difference. When the electricity price, the green line, is below the strike price, they are paid the electricity price plus the difference between the strike price and the price of electricity. So they are paid the green line plus the difference between the red and the green line. Okay, these are the main three ways to do it. But there are other alternatives. Okay, well, we have tradable green certificates, we have auctions. I mean, the nice point is that this red line that you see there, either for a feed-in tariff, which is the total remuneration, feed-in premium, which is the premium plus the electricity price, or the strike price in a sliding feed-in premium, this can be set administratively. This means that the government sets this remuneration, or it can be set in an auction. So let the market decide where to set it. Okay. Well, this follows a traditional discussion in environmental economics, where we have price-based versus quantity-based support instruments. On the right, you see the price-based one, where what you see there is a marginal, long-term marginal generation cost for renewable energy, where the different steps that you see there in colors represent the different costs of different technologies, long-term marginal cost. Of course, you know, you have cheaper technologies and more expensive ones. And well, what you can do is to set the remuneration. This means the price, the euros per megawatt hour, and you know, the actors in the market will come, will generate more or less depending on their cost, and you will get the quantities because of this. Okay, and you can also have an instrument where the quantity is set by the government, such as in auctions, and the market. This means the interaction between the different participants in the auction, also called bidders, set the price as a result of this auction. Okay. Okay. So before talking to auctions themselves, why not just simply to allow the government to set the remuneration? This is administratively set remuneration. But administratively set remuneration has had certain advantages in the past. They have been very good in kickstarting the market. They provide low risk for investors. You know, well, they have shown to create markets, to be positive for the value chain, and also they have been shown to be very good for different types of actors. So not only for the large actors, so for the large firms, but also for the smaller ones. So an actor diversity is created through this instrument. But they have a main problem. When the government sets the level of remuneration, the government does not have information on the cost of the technologies. The cost of the information on the cost of the technologies is on the hands of those who are being regulated. This means the investors, the generators. Okay, so there is an asymmetric information problem, because if the government tries to identify what are the costs of generating electricity with these technologies, well, hello?
Sorry.
Keep talking, Pablo.
Okay, well, then the government may get it wrong, because, you know, the investors and the electricity generators may tell the government a cost which is higher than the real cost. There's an incentive to do that in order to get a higher subsidy. Okay, so, you know, this asymmetric information problem has been very, very acute in the last 20 years, especially in the last 10. This has led to to booms. This has led to excessive support for technologies. This means that the remuneration has been not only above the cost, which is, you know, remuneration is supposed to be above the cost, but not excessively above the cost. So a little bit above the cost, but not, you know, very high above the cost. And this is what has happened for some technologies in some countries in the past, you know. So what has been the problem with this is that, you know, in some countries we have experienced booms. This is the case of Spain, where you see there, this is for solar PV. Okay, on the left, you see that we applied an administratively set feed-in tariff until various few times, I mean 2012. And what you see there is that suddenly there was a boom, a solar boom. And the reason behind that boom, you can see that in 2008, there was 2,708 megawatts of PV installed in that year. This is the amount of installed capacity, annual installed capacity, and you see there's a peak. This peak is due to an excessive, too generous feed-in tariff for that year. Okay, compared to the cost. The cost went down, but the feed-in tariff did not respond to those costs going down. So this created, you know, a very profitable investment for those deploying renewable energy. And this, on the other hand, led to, on the right-hand side, to a very high increase in the support cost, partly related to solar, you know, which went to about 3,000 million euros for 2009. 3,000 million euros is about, I would say it's 0.3% of GDP in that year. Okay, well, I mean, it may not look a lot to you, but 0.3% of a GDP just dedicated to support PV in 1 year, it was deemed very concerning amount by the government at the time, and it was, you know, that was the reason. So, you know, it was decided by many governments to shift to auctions in order to limit this problem. You know, you can see there a graph from IRENA where you can see that in the pink you see the feed-in tariffs. This means the administratively set remuneration. You know, it has increased over time, but you can see in the orange columns, which is auctions, you can see that the increase in auctions has been greater. We do not have the data for the last 4 years because this was from IRENA 2018, but I can tell you that today there are more countries using auctions than administratively set feed-in tariffs. Okay, so what are auctions in reality? How do auctions work to promote renewable energy? Well, renewable energy auctions, we should be clear that renewable energy auctions are procurement auctions. What does this mean? Well, when you think of auctions, you tend to think of, you know, someone selling, for example, a picture, okay, or a Chinese jar, right? You imagine Sotheby's, you imagine any other, you know, shop selling things, okay? And this is usually an auction which goes up. This means that the price is offered and the one who gets the highest price, who proposes the highest price, gets the picture, okay? Renewable auctions work the other way around. This means that what you have there is an auctioneer, you have the government providing support, and you have many bidders, many participants. The participants are renewable electricity investors, renewable electricity generators. Okay, and what they propose is a lower, you know, a low amount of subsidy. The one who gets the lowest, I mean, the one who submits, the one who proposes the lowest bid wins. Okay, so it is an auction, you know, to procure renewable electricity, where, you know, the one who proposes the lowest price wins. Okay. Okay, well, this is like a small example to show you this in broad terms. You have a demand, say 3 megawatt hour. This is set by the government, and you have 4 bidders. each offering, different quantities, 5, 7, 8, and 9 euros per megawatt hour. Well, the three who offer the lowest prices win. This would be those the bidders who are awarded, which are to the left of the figure. You can see that. Okay. Okay. So how much volume was auctioned in the last couple of years? Well, actually, 2017, 2018. With the last, this is the last data we have as for today, taken from IRENA as well. 110 gigawatts. This might not seem a lot to you. This is about 2/3 of the current electricity generation capacity installed in Spain. So, I mean, it's relatively high. And you can see that the per country, I mean, not per country, per continent and per technology. You can see that most of this has been auctioned in Europe. Volume auction for renewable energy has been mostly in Europe and Asia. And also, well, you see there, Africa is a little bit less on that, but still non-negligible amounts. And you can see that in terms of technology, solar PV is and wind onshore are the ones, the technologies most awarded in the auctions. These are all also the technologies, the renewable energy technologies, which are most mature. This means that they have the lowest cost of all renewable energy technologies, virtually everywhere. So why are auctions good? Well, since bidders have to compete for a given subsidy and they have an incentive to bid very low, well, this provides support, this minimizes support costs. So under auctions, the government usually provides the lowest support cost than in administratively set feed-in tariff. This is what auctions are supposed to achieve, okay? They may not achieve it in sometimes because this depends on the competition between the bidders, but this is what the aim of auction is, to minimize the cost of support. Also to control expansion, because, we said that the government sets a demand, 3 megawatt hour, so this, the government, by setting this demand, they control the expansion of renewables, which might be fine, especially if we want to have a gradual transition over time, okay? So, also bidders have an incentive to provide the lowest cost, and the lowest cost bidders usually win in the auction because they can provide the lowest bids, okay? This also leads to a static efficiency. This means that the minimum generation costs are achieved. There might be also an incentive for innovation. I put a question mark there because this issue has not been analyzed in the past. I am analyzing that currently in a European Union project, but they are, in theory, they could incentivize innovation as well. Well, you can see actually that the bids, the weighted average bids in auctions have been going very, down and down, down. What you see there is the weighted average bids in the world in the period 2010-2018 for solar PV in orange and wind onshore in gray. You can see, especially for solar PV, a strong reduction over time. This is not only due, or not mostly due to auctions, but it is also due to the technology, the reduction in the cost of the technologies. I mean, solar PV has experienced an impressive reduction in its cost, mostly due to learning effects. And the good thing about auctions is that auctions have been able to capture those cost reductions over time. Okay, the cost reductions for wind have also been very important, very relevant, but they are less impressive. Okay, so auctions have also had some problems. One of them has been, or the most important one, has been under contracting. This means that, and also underbidding. What does this mean? This means that bidders have an incentive to a state to propose a very low bid in order to secure an award, in order to secure that they are winning in the auction. But if they propose a very, very low bid, and this bid falls below their cost, of course, no one would bid below their cost, but they can do so, you know, because they, you know, when the auction is proposed, they know their cost, but they do not know their cost when they will build the project. And they will build the project in a couple of years or maybe 5 years' time. So they are proposing a bid according to the expectation on their cost in 5 years or 2 years' time. Okay, so they may roughly bid below their cost. If they do that, this is called underbidding. They find out when they are going to build the project that their bids are lower than their cost, and so they decide not to build the project. Okay, there may also be delays. You know, this is caused by many factors. You know, it can be caused by, for example, not having administrative procedures. I mean, administrative permits, not having the grid connection point. You know, many issues might be due to this, or maybe there is a supply chain bottleneck in terms of provision of given parts for the renewable energy project, whatever. This has been proven in the past, as I will show you some data on this from IRENA. They have also been shown to be dynamically inefficient. What does this mean? They have not supported the lowest cost, I mean the less mature technologies. The least mature technologies are usually not promoted by auctions because auctions encourage the lowest cost technologies, and those with the highest cost are of course usually not you know, awarded in auctions, especially if we are talking about technology neutral auctions. They are also detrimental for small actors because they provide higher risk. I mean, they usually entail higher risk, and small actors cannot bear this. And well, there may be a problem with low competition. What does this mean? It is extremely important for the success of the auction that the competition is very high, is enough. If there is not good competition, this means that if there are few actors, few bidders, or if bidders are able to communicate, you know, to agree between themselves, which is forbidden, this is called collusion, well then what we could expect is very high bids. So, you know, we would not achieve the advantages that auctions are supposed to achieve. I show you some data, you can see this later, but some data from IRENA on under contracting and under bidding. You can see there for India, the total amount that was awarded, and you can see in green the amount that was actually built. For this is for national and also regional or state auctions in India. You can see delays in several countries. This has happened in solar and wind in some countries. The projects built on time. This means the green line have not achieved 100%. So you have a delay, the orange, and you have also abandoned or unknown state for some of the projects. I have to say that the delays are more usual, are more common than abandoning projects. Okay, but delays also happen. You can see as an example of low competition leading to high bids. This is also taken from IRENA. You can see the case of Germany. The gray line shows you the level of the bids, and you can see that they went down, the bids went down until they went up, and they went up, and you can see down. Why? Because the volume submitted, this means the volume, the number of people going to the auction was very low compared to the auction volume, to the volume which was auctioned. If you go, say 1,200 megawatt go to the auction, in an auction where 1,000 megawatts are auctioned, well, this means that you can expect low competition. The lower the degree of competition, the higher the amount of bids. That's quite obvious. This is what happened for solar PV auctions in Germany. Okay, so are auctions good or bad? Some people like to ask this question. I think this is a naive, nonsensical question. For me, it is wrong. Some people love auctions and some people hate auctions. I neither hate nor love auctions. I think they are a good instrument. They can serve the purpose, especially if auctions take into account the contest conditions where they are applied, the goals of the country, and they are designed according to these goals, and according to some criteria, they can be good or bad. What are the context conditions before you implement an action? You have to take into account these context conditions. What are the characteristics of the country? What are the characteristics of its electricity system? Is there a local value chain for renewable energy projects? Once you have this, what do you want? It will be something like that, right? The preconditions. I mean, the context condition is, so to say, the preconditions that we would need in order to set the goals for the auctions. But there are also some preconditions for successful auctions. We need to have renewable energy targets, energy policy targets, in the long term, which give signals to investors. We need to have enough competition. This is key. This is crucial. If we design an auction where the volume is very, very high compared to the people that will go to the auction, then this will certainly be a failure, because we will have not enough competition. And if we do not have enough competition, we will have high bids. And if we have high bids, why did we implemented auctions in the first place? So we need to do a market analysis of what the people going to the auction will be. We need to coordinate the different procedures. If we do an auction, but we do not coordinate with the administrative procedures or the grid access procedures, people winning in the auction may not have the administrative permit or the grid access permit. And the other way around, people may have the administrative or the grid access permit, but not win in the auction. This is, for example, the case in Ireland in the 1990s, and this doesn't really make sense, right? So we need to coordinate this. And we need to have transparency. Auctions need to be transparent, need to be simple. You need to provide all the information. For example, very good cases in this regard are the Latin American auctions. Peru, Mexico, Chile, they provide all the information in their website. You need to have that in order to stimulate, encourage the participation. If you encourage the participation of people, you will get a lot of people, you will get a lot of competition, and you will get a successful auction. So, and also we need to take into account what are the goals of the government. Is it to expand renewable energy capacity? Great. Then we will design it in, to maximize that. But is it to contain support costs? Probably yes, and probably in addition to expanding the renewable energy capacity. Is it to have a wide diversity of actors, not only the large ones, but the small ones? Okay. And is it to create a local industry? Well, I mean, if you have all these goals, then you will design it accordingly. But bear in mind that these goals may trade off between each other. If you want to promote actor diversity, for example, the small actors being also there, small actors have lower economics of scale. If they have lower economics of scale, then they will require a higher bid. If they require a higher bid, you will have higher support cost. Okay. Also, if you have small actors, probably they are not so so professional, or they might be professional, but some of them may not. So if you have very small actors, this is good for the energy transition. This is necessary for the energy transition, but this may be problematic in other senses. Okay, so the governments have to take into account these trade-offs and identify what are their priorities. Okay, and of course they can judge the functioning of the auction according to those goals, which in terms of criteria are the ones that you have over there, which are really, in a way, are a repetition of those goals. So auctions are here to stay. Why are they here to stay? In Europe, we need to support renewable electricity projects if they need support with auctions. We don't have any other chance to do it. Okay, according to the EU state guidelines on environmental protection and energy, and also according to the directive, Renewable Energy Directive, you can see Article 4, and there you can see that it is the way. So we need to focus on auctions, but we have some degree of flexibility. And the flexibility is in the details of the auction. There are many alternatives to choose from. We can design the auctions in many ways, or we have at least many alternatives. Okay, Some of them are there. You can see, you know, general auction design elements. We have a lot of choices. You know, I will go through some of them in this, through the most important of them. You have a lot of information also in the AURES project websites. I will show you later, and also in IRENA. But what I did an analysis of how auctions have been designed around the world. So I look at 67 auctions in 48 countries. I use a lot of case studies on auctions, official documents, you know. And I try to get all information on how auctions have been designed around the world. And well, I did this as part of two European Union projects, AURES, which ran from 2015 to 2017, and AURES 2, which ran from 2018, and it is currently we are currently there working on it. Okay, these are two European Union projects. There's a lot of information on their websites, and if you are more interested in renewable energy auctions, I would, you know, encourage you to look at IRENA, International Renewable Energy Agency, and also at the AURES project. And I also published some of these findings in papers, you know. Well, this is what I did. So. What are the options to design? What are the options to design auctions? Well, we can distinguish between many categories. Okay. For example, how do we define the volume in an auction? Do we define it in terms of generation? Do we define it in terms of capacity? We define it in terms of budget. Okay. How do we define it? Well. What we can usually do is to define it in terms of capacity. And each alternative has its pros and its cons. If you define it in terms of budget, this means a total budget is provided for support, then you may not achieve renewable energy targets in terms of capacity. So I would think that it's very important that probably you would do it in terms of capacity or generation. Okay. This provides a clear message to the supply chain on what will be the market for that technology. And also, if you do it in terms of capacity, this also provides a very effective auction in terms of you can judge effectiveness since the start. Okay. A main thing in volume, I think I addressed this before, is how to set the support level. How to set the volume level. If the volume is too high compared to the people going to the auction, then we will not have any competition. Competition will be very, very small. High bid prices would result. If the volume is very, very small, this is bad in terms of the energy transition. We are not introducing enough renewables into the system, but it is also bad in the sense that probably we will have a lot of competition, which is good, but maybe too much competition. This means that there's likely to be a problem of underbidding, a very, very aggressive bidding with very, very, very low volumes, especially compared to the people going to the auction. I would support that there is a schedule for the auction. You know, we need, this would be important. We can set as a schedule. This means that auctions, we know what auctions will be there for the next 10 years. Or the government just, you know, may conduct auctions whenever they want, based on an ad hoc basis, you know, just infrequent ones. I think that the schedule of auctions is good because this encourages participation. This provides a signal also to investors and also for the whole supply chain. So I think that it would be important to have a schedule of auctions. Regarding the realization period, it can be very short or very long. If it's very short, you know, those winning in the auction have a very short time to build their projects. Well, they may not build their projects on time, so there might be a delay. But if the realization period is very, very long, there is a problem that since bidders have bidded according to the cost that they will have, or they are expected to have in the long term, that they will bid wrongly. This means that they will bid below their cost. If they do so, then there is a risk of underbidding and then ineffectiveness. Then it is important that you require people going to the auction to provide some, insurance that they will build the project. Okay, you can ask for material and financial pre-qualifications. Financial pre-qualifications are big bonds, that they are deposited, and if you do not build the project, you lose your bid bond, okay, that you have given. Material pre-qualifications refer to, for example, can be faced by the project. A connection point is required, an administrative permit is required, whatever, so that, you discourage those people who are just going there for speculative reasons, but are not really going to build the project. Okay, and of course, the level of stringency is very important. If they are very stringent, if the material or financial pre-qualifications are very stringent, then you would ensure that the project will be built, but probably you will discourage bidders. This means that there's always a trade-off. So it will be good for effectiveness, but it will be bad for the minimization of support costs. But if the level of stringency is very low, you do not require anything, you will probably get very low prices, but many of these people may never build the project because, if they do not build it, they will not have to pay anything. And they were not required to show that they could, build the project, that they had the technical capacity or whatever to build the project. So again, problems. Pricing rule, you can ask, you can provide a uniform level of support for all winners in the auction, or winners are awarded the price that they bid in the auction. So the first one is, the pay as bid. The pay as bid is if you and we can come back to our example here. In a pay as bid auction, the 3 awarded bidders would get 5, 7, and 8. Okay. In an uniform price bid auction, the 3 guys, the bid 1, bid 2, and bid 3, would get €8, the bid of the last awarded auction, or the bid of the first rejected auction. This means either 8 for all of them or 9 for all of them. Okay, but they all the awarded bidders get the same amount. This has its pros and cons as well. According to the theory, and I would spend a lot of time to say this, but when you have uniform bidding, there is a risk of maybe too aggressive bidding, and especially there is an uncertainty on the level by the generators, on the investors that we will get, because they will receive the marginal price. Price ceilings. It is important to have price ceilings in case there is not a lot of competition. This would mean that we would have a very high price above the ceiling price. And if we have that, this would mean a high support cost. Should we organize auctions irrespective of the technology, or should we organize technology-specific auction? This is also a very important decision. If you organize auctions in which all technologies, renewable energy technologies, can participate, of course, there will be higher competition, higher efficiency, and probably lower support cost. Okay? But the problem with this is that the less mature technologies will not be awarded. This means that this is precisely the benefit of specific auctions, where you promote technologies with different maturity levels. Okay, and you can also adapt for other goals, such as local industry and system integration. What about diversity geographical? Do you require projects to be built in a certain location, or would it be better just to, leave generators and investors decide where to locate their projects. Pros and cons: if you decide to, if the government decides where to build the projects, maybe the government does not have the best information in terms of where the resources are best. Okay, so you know, this would lead to maybe places where which are not the best in terms of the highest renewable energy resource. But on the other hand, you minimize the cost of the grid, because what you do, the government knows where the grid is, of course, and they may decide to set the auction where the grid has, you know, where the connections to the grid are. And this would be also very important. This is exactly the case of auctions taking place in sub-Saharan Africa, which are not geographically diverse, but the government, in one way or another, sets the place where the auctions, I mean, where the projects should be located. This is, I'm talking about, for example, Zambia, okay? Also, you can require local content rules. Okay, this means that the equipment for renewable energy projects has been built, has been manufactured in the country. You know, this has advantage that you can stimulate, you can encourage a local supply chain, but it has the disadvantage that the local supply chain might not be very efficient compared to foreign one, and this would mean higher costs. And if you have higher costs for the equipment, you also have higher bids. And if you have higher bids, you have higher support costs. So again, a trade-off here, okay? And you can remunerate generation, you can remunerate capacity. If you remunerate generation, this is better. Why? Because what you do is you give an amount of money per megawatt of hour of electricity being generated. If you do that, you encourage the efficient production of the plant, okay? Rather than just say, well, if you put, say, I don't know, 20 megawatt wind onshore plant or 100 megawatt onshore wind plant, then you will get, you know, a lump sum amount, okay? That does not encourage the efficient functioning of the projects. And a generation-based remuneration does. Okay? And we talked about the different types of remuneration forms before. Selection criteria, renewable energy auctions can be price only. This means that only the price is important, or they can be multi-criteria. You can add, you know, in addition to the auction, the awarded bidder can be based on the contribution, for example, to the local economic development, or to local industry, or, you know, whatever. Okay, so it has its pros and its cons. Price-only auctions usually lead to lower support costs, lower bids. But multi-criteria allow, you know, relatively low bids, you know, higher than with price-only auctions, of course, but encourage also other social goals, like creation of a value chain, okay? For example, in sub-Saharan Africa, you mostly have price-only auctions, but you have a very good example of a multi-criteria auction in South Africa. You know, I refer to, by the way, to sub-Saharan Africa because I did a lot of analysis for Uganda, Ghana, Zambia, and South Africa, okay? These 4 countries. Also, you can have single item versus multi-item. This is less important. You know, multi-item, you have many megawatts, many products, and single item is usually refers to a given technology, offshore wind or concentrated solar power. Okay. Yeah, well, you can also have static auctions where everybody talks to each other and they know each other's bids. Or you can have static auctions where you give a sealed bid. Just you give your bid in an envelope, which is opened by the auctioneer, and you do not know what others have, what others are bidding. It has its pros and cons. Dynamic auctions favor the agreement between the different bidders, and they favor collusion. You know, and so most countries use a static seal bid envelope auction. Well, I did this analysis, and I will show you this, and I will finish probably because I think I'm kind of out of time with this. Regarding the volume, most countries, most of the auctions that I looked at, the 67 auctions, most award the volume in terms of capacity. Surprisingly, most auctions do not define a schedule. You may wonder why. We can talk to that later, but probably, this gives more flexibility to governments. Most technology are technology specific. So this means that you have an auction for wind, another auction for solar, another auction for biomass. You do not have a single auction where all the technologies compete between each other. This is the most common design element. Okay. Then, regarding geographical diversity, some countries use neutral, some countries use diverse, geographical diverse auctions. There is no clear pattern in this way. Many countries, most countries do not have local content requirements. Do not require that the equipment is manufactured locally. Most auctions, I would say, or an overwhelming majority of auctions are generation based. So they, what they do is that they remunerate generation. They do not remunerate the capacity installed. They remunerate the generation from the project, the electricity generation being generated by the project. Okay. Most use of feed-in tariff instead of a feed-in premium, but this is changing quite a lot. In particular in Europe, we are using more feed-in premium now. Selection criteria. Well, most auctions are price-only auctions. Multi-criteria are relatively few. Most are multi-item. Most are static. So, closed envelope. You do not know what others are bidding. This is the governments are very worried about the possibility that bidders agree between each other. So this is also, an important design element. Then we also have pay as bid. Most bidders get what they bid for, not the marginal price of the last awarded bidder or the first of the rejected bidder. And also most use a ceiling price. So winning bidders cannot receive more than the ceiling price. Okay. Trade-offs are unavoidable. I was going to talk a little bit about this. You can see the case of Mexico. In Mexico, it was interesting because what we had there was in the first auction, bidders were encouraged by the design of the auction to locate their projects in the places where the electricity nodes were less saturated. This means that in the places, with less saturated points. And the issue was that most projects did not locate in the places with the best resource. You can see that for both solar PV and wind offshore. This is for solar PV, this is for wind onshore. You can see that the darkest areas are the places with the best resource in terms of wind, and projects are not located there. The triangles are up and down. This means the first and the second auction. You should look at the first auction where there was this location specific measure with the vertex of the triangle looking upwards, and you can see that this was the case. Okay, well, just to finish, I think that there's a lot of trade-offs. That, we have priorities, we have goals, but I think that there is some. I would recommend some best practices. I would set the volumes at appropriate levels. I would include a schedule for the auctions. I would include a stringent pre-qualification requirements and penalties. This should be stringent in order to discourage speculators and discourage the non-realization of projects. I think that technology is specific. I would go for that. I would prefer to remunerate generation instead of remunerating capacity or investment. I think static auctions have worked very well. I would prefer price only versus multi-criteria auctions. I think that the realization period should be set at a appropriate levels, neither too long nor too short, and volume should also not be neither too large nor too low. And finally, I think it is extremely important, also as shown by many countries, including Spain and Portugal, to coordinate the auction procedure, the administrative permit procedures, and the grid connection procedures. This is extremely important for the success of the auction. Well, this is it. I encourage you to look at also some of my material I was going to talk about, but I don't have time, on the design of renewable energy auctions in sub-Saharan Africa. There is some material that you can look at in the references. As I said before, please go to IRENA to know more. They have a lot of guides on how renewable energy auctions work. Also, there are ORES and ORES2 projects funded by the European Commission, in which I have participated. I am participating, provide a lot of information, and other material. And well, this is it. Thanks for your attention. Now I'm if you have any question or comment, I will be glad to answer.
Okay, thank you very much, Pablo. There are a lot of questions. I asked you the first one, the first. For the auctions, who sets the benchmark? And the second question is, to make auctions transparent and competitive, would stakeholders' analysis and involvement play a significant role? If yes, how? Would you mind?
Yes, sure. Yeah, of course. Yeah. Well, who sets the benchmark? I assume that you mean who sets the volume in the auction. Well, this benchmark or volume is set by the government, by the auctioneer. And what is it based on? Well, it is based on you may have long-term targets. For example, in Spain we have to install 50 gigawatts by 2030, and we are going to use auctions from now to 2030. Well, the government can decide the amount, the volume that it will be auctioning each year, and this will depend on the total amount that we will have to be deployed by 2030. Okay, so I assume that you mean the benchmark by this. Auctions being transparent. This is very good, very, very good question. Thanks a lot. Thanks a lot for this question. It is not very easy to answer, but yes. Somewhere. Well, I mean, stakeholder participation is extremely important, but it has limits. Okay, how it should be done, in my opinion? Well, the way it should be done is that the government should draft, should publish a draft of the auction and then send it to different stakeholders. And different stakeholders could give back their opinions in their writing, and of course, different types of stakeholders will have very different positions. Okay, but the government, should design the auction, looking at the science behind it, looking at, the data and experts in auctions. Okay, if they just, are totally influenced by a given actor, then we will have an auction which will be very good for that actor, but it will not be good for society. So they should hear the stakeholders, but we should be careful, that there is not a regulatory capture by a given actor. So it's kind of difficult to do it, but you can do it. You can, of course, hear the people, but at the end of the day, you have to make decisions. And these decisions, should be based on, the rules, the good rules of design. Okay, and I think this is also important, and also on the priorities of the government. Okay, in Denmark, or for example, they have this, and also in South Africa, they had these meetings where, the government gathered with all the people, all the stakeholders, and I mean, I think this is fine, but I think that we should avoid the risk of regulatory capture. If we do not, if we have auctions which do not have that risk, which are designed like that, we will not get very good auctions.
Okay, thank you, Pablo. We are running out of time, but there are some other questions. The first one is how can auctions contribute to the development of electricity access in sub-Saharan Africa? And another one is what is the role of central government and funding partners in energy auctions? What are the critical considerations?
Yeah, okay. Well, how can we, thanks a lot for these questions as well. How can we auctions support the development of electricity access? Well, I mean, auctions work for what they are, you know. Auctions will not solve everything. They will not solve the access problem unless there is an additional regulation, you know, requiring access, you know. So auctions should be coordinated with this access regulation, but they should not, you know, establish guidelines for this access. So they are complementary regulation. Okay, auctions are good for what they are. They are good to get a given amount of renewable energy being deployed at the lowest cost. Okay, if you look at how this was done in sub-Saharan Africa, well, the government in Zambia, for example, set the place where the project should be built. And it was very close. It was in Lusaka, 200 kilometers south of Lusaka. And, you know, they set the place because it was very close to the grid. So they solved the access problem like that. And then, you know, they auctioned 250 megawatt project. Okay, so this is important. The second question is also very important, funding partnerships. In sub-Saharan Africa, for example, they have had the involvement of international organizations and also donors. Norway, Germany, the Netherlands, okay? I think this is, they provided quite a lot of support. Of course, they also influenced the design, but I think the auctions there work very well because of this combination of, you know, of funding sources, which, and also the World Bank, of course, the Scaling Solar Program, you know, so this combination of agents, I think it's important. And, you know, I think that they solve one of the main problems, in my view, which is the financing. You know, the risk of financing is, financing possibilities are not very high in this region. So, you know, they solve, or at least they mitigate this challenge.
Okay, thank you very much, Pablo. Your intervention was really, really interesting. So the questions were not answered, will be answered by the trainer, by Pablo, to your emails, okay, afterwards. So thank you again. So now we are going to the second lecture. The lecturer, the training is Carmen Guinea. Are you there, Carmen? Yes, I see you. Yes. Carmen is a senior industrial engineer of Naturgy. Naturgy is a multinational group operating in 28 countries and with more than 18 million customers. She's talking about some cases studies based on her experiences in Naturgy. Thank you very much, Carmen. I pass the floor to you.
Okay. You hear me?
Yes, sure.
Okay. So I should. Should I get the? I cannot start sharing my.
Yeah. Click on compartir.
Sí. Yes. here.
Okay, that's it. Thank you.
Okay, good morning all. My presentation is related to the projects developed by my company. My company, I am from Netia, what is the gas distribution company in Naturgy Energy Group. My presentation is related to the projects developed by my company in biomethane production. These projects start in the production of biomethane. I mean, the projects that were installed on sites where the biogas was already produced in anaerobic digesters on landfill. Therefore, we didn't have to invest in the biogas generation. But first, we will do a quick review about the main concepts related to biogas and biomethane. That is important to understand the plan. What is biogas and where does it come from? Biogas comes from anaerobic digestion of organic matter by means of bacteria. The process has two main phases: acidification of the organic matter and transformation of the organic matter into methane with the bacteria. This process takes place inside an hermetic tank in order to avoid air to get in and methane and nitrogen emissions to the atmosphere. The reaction inside have to be anaerobic. Inside the tank, or what is called the digester, the organic matter needs a mixing system and heat. The digester can be built in concrete or plastic materials. For big sizes, normally are built in concrete. This process to digest the organic matter lasts about 20 to 30 days. Normally, these digesters are total mixing because they are the most easy to use. Biogas from this process will have from 50 to 70% in methane. And what is biomethane? Biomethane is the gas produced from the upgrading of biogas. It's equivalent to natural gas with the same properties, heating value, work index, and so on. Therefore, you can use it in the same uses as natural gas, like for industrial process where heat is needed, domestic uses, or even in mobility. Due to the fact that the biomethane comes from biogas, its CO2 emissions are neutral. It comes from the degradation of the natural organic matter present in the nature. How can we produce the biomethane? There are three main ways of producing biomethane, but not the three ways are in the same point of development in the market. The most mature method is the anaerobic digestion of organic matter, followed by an upgrading. Any kind of organic matter can produce biogas in an anaerobic digester and later transformed in biomethane by means of an upgrading plant. The biogas gasification and the power to methane and power to hydrogen are still in developing. The cases I'm going to present are based on the first option, anaerobic digestion, followed by an upgrading. The anaerobic digestion produces a biogas with methane concentration around 50 to 70% in CO2, and in CO2 in methane, and in CO2 around 30 to 50%. Sulfuric acid with concentration lower than 2000 ppm, and siloxanes about 10 to 20 milligrams per cubic meter. Sometimes other contaminants appear, as ammonia, for example. The biogas enters into the upgrading plant and produces the biomethane with concentrations over 95% in methane and CO2 below 2%. Depending on the size of the plant and on the quality of the biogas, we will choose one or other upgrading technology. For example, for biogas without oxygen and nitrogen and flows below 1000 cubic meters per hour, the most competitive technology will be the membranes. While over 1000 cubic meters per hour, sometimes the most competitive technology will be chemical absorption. It depends on each particular case. For biogas flows below 2000 cubic meters per hour, the most common upgrading technologies are the membrane technology, chemical absorption with amines, and PCA, what is pressure swing absorption. Other technologies could be used in particular projects. For example, if there is water available in big quantities, water absorption technology could be used. Or cryogenic technology would be used for biogas with nitrogen or oxygen concentration, that is the case of some landfills. Chemical absorption technology with amine is based on the affinity of the CO2 to the amine. Carbon dioxide is not only absorbed in the liquid, but also reacts chemically with the amine in the liquid. Since the chemical reaction is strongly selective, the methane loss might be as low as 0.1%. Part of the liquid is lost due to the evaporation and has to be replaced. The liquid in which carbon dioxide is chemically bound is regenerated by heating. Two types of compounds are used, monoethanolamine and dimethylethanolamine. If sulfuric acid is present in the biogas, it will absorb in the amine-Scruber solution, and higher temperatures will be needed for the regeneration. Therefore, it's advisable to remove it before absorption in the amine-Scruber. Oxygen and nitrogen are not rejected with the CO2. Therefore, the biomethane will have same concentration for both gases as the biogas. In PCA technology, PCA, pressure swing adsorption, carbon dioxide is separated from the biogas by absorption on a surface under elevated pressure. The absorbing material, usually activated carbon or zeolites, is regenerated by a sequential decrease in pressure before the column is reloaded again. This is the reason of the name of this technique, pressure swing adsorption. An upgrading plant using this technique has 4, 6, or 9 vessels working in parallel. When the absorbing material in one vessel becomes saturated, the biogas flow is switched to another vessel in which the absorbing material has been regenerated. During regeneration, the pressure is decreased in several steps. The gas that is desorbed during the first and second pressure drop may be returned to the inlet of the biogas, since it will contain some methane that was absorbed together with carbon dioxide. The gas desorbed in the following pressure reduction step is led to the next column, or if it's almost entirely methane-free, it's released to the atmosphere. If sulfuric acid is present in the biogas, it will irreversibly absorb to the absorbing material. In addition, water present in the biogas can destroy the structure of this material. Therefore, sulfuric acid and water needs to be removed before the PCA column. Part of the nitrogen and oxygen from the biogas can be rejected. Normally, the limit in the inlet biogas to the upgrading will be for oxygen 1% and for nitrogen 3%. And if you install 2 stages of PCA instead of just 1, the limit in oxygen could be increased to 3% and for nitrogen 14%. This is important for landfills, for example. Membrane technology, as the name indicates, uses the dry membranes made of materials that are permeable to CO2, water, and ammonia, while methane and nitrogen only passes a very low extent. Oxygen permeates to some extent. Membranes can be arranged in 2 or 3 stages. The biogas needs to be pressurized between 8 to 16 bar by means of a compressor. This technology needs a pretreatment before the membranes to eliminate water and the contaminants, as sulfuric acid, volatiles, and water. The membranes are hollow fibers bundled together. They are made of a polymer. Membranes plants have easy and quick installation and commissioning, what is called plug and play. The plant arrives on site in a container to be connected to the biogas plant. The installation costs are smaller than in other technologies. This technology is very easy operation and it does not require specialized skilled operators. The methane recovery is over 99% and the methane concentration in the biogas, in the biomethane, is over 95%. When the membranes are arranged in 3 stages, the methane recovery reaches values over 99%, while with 2 stages, the recovery will be around 95%. The project that we have developed, all the projects that we have developed in my company are all of them with 3 stages in order to recover as much methane as possible. This is the comparison of the main technologies for medium and small size plants. The technology with higher electrical consumption is the membrane, although very close to the rest of the technologies. Chemical absorption needs extra heat to regenerate the amine, but the methane loss is below 0.1%, while in membranes is around 1% and in PCA 2%. Pressurized water scrubber needs water and the wastewater treatment of the effluent. And its advantage is that it doesn't need the biogas pretreatment before the upgrading. PCA rejects part of the nitrogen and oxygen, and this makes it competitive for biogas with both gases in its composition, as in landfills. Therefore, each technology has its advantages and disadvantages, and has its own core market. In each project, the technology to be used has to be carefully selected. Here you can see an estimation of the investment and operating cost ratio for small and middle-sized plants. This data is based on the membranes technology. CapEx ratio includes not only the upgrading plan, but also the pretreatment investment. The OpEx includes the electrical consumption, which is the highest cost, the active carbon consumption, considering 300 ppm of sulfuric acid in the biogas, and the operating and maintenance costs. This ratio is based on Spanish cost. Like, for example, we have considered the electricity cost for 95 euros per megawatt hour. So this ratio has to be looked at it very carefully. As it can be seen, for smaller plants below 1,000 cubic meters per hour of biogas, the CapEx and OpEx ratio depends strongly with the size of the plant. But for bigger plants, these ratios are less influenced with the size. In this data is not considered the biogas production, because our projects, as I have told you before, started with the biogas already produced. Now, I'm going to start with the project that we have developed in our company. The projects are these ones: Vence in the northwest of Spain, Metamorphosis in the northeast, Butarque in Madrid, and Elena landfill in Barcelona. This is the location for them. Vence. The project consists of an upgrading plant for biomethane production from the sludge of a municipal wastewater treatment plant in Coruña. The biogas flow is 100 cubic meters per hour to produce 5.5 gigawatts hour per year of biomethane. The investment was 1.1 million euros, and the biomethane is being used for mobility. During the following months, we will start injecting the biomethane into the natural gas grid. The upgrading technology in this case is membranes. Butarque. The project consists of an upgrading plant for biomethane production from the sludge of a municipal wastewater treatment plant also, but in this case is in Madrid. The biogas flow is 100 cubic meters per hour to produce 5 gigawatts hour per year of biomethane. The investment was 0.8 million euros, and the biomethane is being used for injecting into the grid. We have been injecting since last year. The upgrading technology in this case is amine absorption. Metamorphosis. The project consists of an upgrading plant of biomethane production from the slurries from animals and food industries wasted. It is developed in Lerida. The biogas flow is 214 cubic meters per hour to produce 9.4 gigawatts hour per year of biomethane. The investment was 1.2 million euros of biomethane and is being used in mobility. In the near future, we will start injecting this natural gas into the grid. The upgrading technology is membranes, as in Vence projects. Elena landfill, the project, is in construction these days. It consists of an upgrading of 350 cubic meters per hour of biogas, and the technology is also membranes. The biomethane to be produced will be injected into the natural gas grid, and we expect to be injecting the first months of next year. We will start with Ben's project. The wastewater treatment plant of Coruña produces more than 400 cubic meters per hour of biogas and sends 100 cubic meters per hour to the upgrading plant. This is the view of the wastewater treatment plant, and the white ball is the gasometer. Just beside it, it's the upgrading located. This is the view of the plant installing in the biogas. The wastewater treatment plant collects the sludge into 2 anaerobic digesters. The biogas flow is, as I told you before, 100 cubic meters per hour of biogas, and the biomethane 60 cubic meters per hour. The biomethane has over 95% in methane. With the energy that this plant can produce, you can fill 12 buses or 440 homes from Spain consuming heating, and 1,100 vehicles per year. This is the view of the place before installing the upgrading. We developed the basic and detailed engineering considering the safety and environmental requirements for the place. This is the container where the upgrading plant is located. It has 3 spaces. From left to the right, first the control room, then the process room where the membranes are located, and finally the filters, compressor and chiller. This last space is open to outside. In the following photos, you can see the construction of the plant. The main foundation will be, this is the main foundation with the earth structure and the installation of the main container with the required crane. In the following photos, you can see the pipe works connecting the existing biogas pipes from the plant to the pipes of the upgrading. The installation works were very quick and easy. These are the biogas pipe and the biomethane rejected from the upgrading plant. And the last photo, this is the final view of the upgrading plant. Part of the plant is inside the container and the other is covered just by a roof. There are 3 main parts of the upgrading plant. The pretreatment, which consists of a chiller and a blower. This is the blower. The filtration, consisting in 2 activating carbon filters to absorb the sulfuric acid. Then the biogas already pretreated, it gets into the process. The compressor sends the biogas to the membrane. This is the compressor. And finally, the membranes, the 3 stages of the membranes. The biomethane with the correct quality to be injected is sent to the refueling station and to the natural gas grid. This is the process diagram. Before getting into the plant, the biogas is cooled in a heat exchanger, where there is compressed with a blower from 20 millibars to 200 millibars. After that, the carbon filters absorb the contaminants. Once the biogas is clean of water and contaminants, is compressed by a main compressor. The biogas is then sent to the different stages of the membranes. The concentration of methane begins with values over 50%, increases after the first stage to values over 70%, and ends with values over 95%. The temperature of the biogas starts in values around 35 degrees, depending on the season, and it has to be cooled twice below 5 degrees before getting into the membranes to reduce the water content. The membranes can be damaged and the biogas has to be eliminated from water and contaminants. And the pressure starts in 20 millibars, that is the pressure in the digesters, and go to 16 bar after the compressor. The biomethane to be injected into the natural gas grid has to have a pressure according to the pressure of the grid. In this project, the biomethane has to have 16 bar. The activated carbon filters eliminate the volatile organic compounds and sulfuric acid and siloxane. The sulfuric acid is monitored each 30 minutes before, in the middle, and after the carbon filters, and the oxygen continuously monitored. The system includes safety valves to avoid overpressures of the system. The upgrading process in this plant is controlled by the concentration of CO2 in the biomethane. The goal is to obtain CO2 below 2% by means of regulating the control valves. If valve 500 closes, the biogas compressor increases the discharge pressure, looking to obtain the objective in 2% in the CO2. If quality of biomethane does not comply with the required quality, valve 500 would open and would send the biomethane back to the suction of the compressor, increasing the pressure. Another control loop is the methane in the permeate stage 3. Valve 610 will open or close to maintain the minimum methane concentration in the permeate of stage 3. These are the basic control loops. Pressure, temperature, and water dew point are the inlet main control points before getting into the compressor. The upgrading plant, and therefore the compressor, could be controlled by 4 different ways. Maintaining the biogas level in the gasometer, in case, for example, you have motors consuming from the gasometer. Maintaining the biogas flow at the upgrading inlet. Maintaining the biomethane flow to be produced, or maintaining the biomethane level in the ejection system to the natural gas grid. Inside the compressor system, there is also control of the water dew point by means of condensating the still water content in the biogas. Therefore, reheating after the biogas is required, and after this, hydrocarbon and particle filtration is installed. The compressor includes a frequency converter that increases or decreases the motor speed in order to increase or decrease the discharge pressure and the flow of biogas. The biomethane conditions and quality are monitored by means of these instruments and analyzers. Sorry. Here, the compressor is. The biomethane conditions and quality are monitored by these analyzers and this control system. The biomethane is shared among the refueling station, the natural gas grid, and the gasometer. When the biomethane does not comply with the required quality, it is returned to the gasometer. In this wastewater treatment plant, the upgrading plant is monitored by the PLC with the SCADA system. This is the PLC and the SCADA system. This is the communication drawing, the SCADA system that you can see from the screen, and the control system. The biogas and the biomethane quality is monitored by the following analyzers. This is the multi-analyzer for biogas that measures the methane, CO2, oxygen, and sulfuric each 30 minutes. And the pretreated biogas, each 30 minutes it measures the sulfuric and the methane in the off-gas. The multi-analyzer for the biomethane is Union, and it measures methane, CO2, oxygen, and sulfuric. This is the analyzer. The water dew point that is critical for the compressed biogas and for the membranes is measured with this instrument. The auxiliary equipment installed in the plant, we have a chiller to cool the biogas and the buffer tank for water, a recirculation pump and the heat exchangers, one for the biogas and another one for the compressor. Besides, another auxiliary and safety systems are installed in this plant, as the instrument system, the air conditioning, and the safety devices. as the gas and smoke detectors. We have methane and smoke detectors in the control room and in the process room. Besides, the ventilation in both rooms are ATEX blowers. And we have also acoustic and visual alarms to protect the system. As I told you before, one of the main disadvantages of the membranes plants is the electrical consumption. The main consumers are the biogas compressor, the chiller, and the blower. In this plant, the total installed power is 59 kilowatts, although the consumption is 31 in the maximum case. This is due to the fact that the main consumers has to have ATEX motors, and therefore the installed power has to be nearly twice of the consumed power. The ratio of electrical consumption in this plant is 0.33 kilowatts-hour per cubic meter of biogas treated. This plant can work normally from 50 to 100 of the nominal capacity, with flows over that 50% of the electrical consumption is much higher because the compressor cannot work with the frequency converter. Therefore, the electrical consumption is higher. This is the refueling station and the bus, a bus filling in this refueling station. The refueling station includes a capacity of 1,020 liters and 2 compressors for 18 cubic meters per hour each one. This is the final layout with the injection system. The gas entry unit is this container, the smallest one in the back. This is the upgrading plant, and this is the container for the gas entry unit. This is the one that is going to be installed in the next months. It's already built. This is the drawing of the gas entry unit with the equipment located inside the container. There are 3 rooms. 1 safety room for the electrical and control systems, 1 for the regulating system, and 1 for the compressor. The project requires a booster compressor because the natural gas grid in this area has a pressure of 16 bar, and the biomethane pressure at the outlet of the upgrading is 15 bar. Therefore, it requires a booster compressor to increase to the 16, over 16. Butarque project. This is the second project treating sludges from a municipal wastewater treatment plant that we have developed. The biomethane is injected into the natural gas grid network. One of the objectives of this project is to develop the guarantees of origin for renewable gas in Spain and to demonstrate the eco-efficiency of renewable gas for mobility. Butarque is the 5th municipal wastewater treatment plant in Spain. It has a capacity for 1.7 million people. This sludge sent to the anaerobic digestion comes from the primary and secondary sedimentation of the water line from the wastewater treatment plant. Inside the digesters, the sludge is mixed and heated until 37 degrees. The biogas produced from this plant has a methane concentration around 60 to 64%, and the rest is CO2. The plant has very small concentration in sulfuric acid. This plant has 3 digesters, each one for 10,000 cubic meters. From them, the upgrading received 100 cubic meters per hour of biogas and produced around 50 cubic meters per hour of biomethane for injecting into the grid. This is the 9% of the total biogas produced in the wastewater treatment plant. 90% of the biogas is sent to 3 cogeneration motors, each one around 1 megawatt, that produces energy for the wastewater treatment plant consumers. This upgrading plant produces enough energy to feed 11 buses or 400 homes or 1,000 vehicles per year. That is 5 gigawatts hour per year of energy. This is the process diagram of the upgrading plant in this project. Here, the upgrading technology is chemical absorption with amine. As I told you before, the affinity of the amine to the CO2 makes the separation between the methane and the CO2 easier. Carbon dioxide is not only absorbed in the liquid, but also reacts chemically with the amine. The biogas first is compressed with a blower from 15 millibar to 200 millibars. After is cooled to 15 degrees to condensate the water that comes with the biogas. Remember, the biogas from the anaerobic digester is saturated in water. After the water condensation, the biogas passes through two carbon filters to absorb the possible contaminants, and after, the biogas already pretreated goes to the absorption scrubber, where the biogas passes counter-current with the amine solution. Biogas goes from the bottom to the top, and the amine solution goes to the top, from the top to the bottom. The amine solution saturated with CO2 is sent to the desorption scrubber. There, with heat, reaches the boiling point over 125 degrees, and CO2 is free to the atmosphere. This heat is produced by a biogas boiler that is also part of the upgrading plant. Therefore, in this process, part of the biogas is consumed to produce heat. The amine is condensated and returned again to the adsorber scrubber in a closed loop. Some water is lost and therefore has to be replaced to the circuit. The amine consumption is very low. Frequently, the concentration of the amine is checked in order to maintain the 30% in the circuit. The biomethane with over 99% in methane concentration and saturated in water has to be dried before being sent to the natural gas grid. Biomethane to be injected into the grid has to comply with a water dew point below 2 degrees. The biomethane compressed to 6 bar is fed to the dryer columns and finally sent to the gas entry unit. This is the normal quality register of biomethane injected into the grid in this project. You can see the methane concentration of 99.7% with less than 0.2% in oxygen. The biomethane quality is controlled continuously via chromatograph. This is the general view of the plant. The digesters in number 1, the upgrading plant in number 2, number 3 is the gas entry unit, and number 4, the pipe of biomethane to the natural gas grid. This project includes also the refueling station that takes gas also from the natural gas grid. 10 meters down from the injecting point into the grid, the natural gas is sent to the refueling station. This was in order to check if the biomethane injected and mixed with the natural gas from the grid could affect vehicles or not. As far, vehicles haven't any problem using this natural gas. This is the process diagram of the gas entry unit. It has 2 lines for regulating and measuring the biomethane flow. Each line consists of a filter, a regulating system, and a fiscal flow meter. The other line is for returning the biomethane when it's rejected due to its quality. The rejection is to the gasometer. This is the gas entry unit from inside, and the regulating system that controls the pressure of the biomethane and reduces it from 5 bar to 3 bar. That is the pressure in the grid in this area. This is the PLC screen that controls the process. This is monitored from Energia Control Center in Barcelona. This is the biomethane already injected into the grid during the first year of this project. The energy already injected could feed 511 homes per year, or 204 vehicles, or 5.7 buses in a year. The following project is Metamorphosis project. It's located in a small village in Lérida called Vilasana, in a pig's farm. There, they produce around 200 cubic meters per hour of biogas from the digestion of about 45 tons of wastes per day. 45% of the wastage comes from pig slurries, 50% from sludge of the wastewater treatment plant, and the rest 5% comes from food industries. This is the farm, and this is the upgrading plant. The 3 anaerobic digesters and the upgrading plant. In this project, the biogas flow is around 200, and the biomethane produced around 120 cubic meters per hour. That means 9.4 gigawatts per year, gigawatts hour per year, with a quality enough to be injected into the natural gas grid, where is methane over 95% and CO2 below 2%. This is the basic process scheme. The equipment in the upgrading plant are basically the same as the plant in Ben's project. In this project, the biomethane produced has been used for mobility, and it will be injected into the natural gas grid in the next future. During the design stage, we review and approve the basic required data as the civil work drawings, as this one, and the general layout. The pretreatment skids were located out of the container, as close as possible to the upgrading. The upgrading was also located near the farm entrance to make easy the access to the filling station. We reviewed the safety and ethics requirements of the project, establishing the required distance among the different facilities. This is the ethics drawing that is very important part of the project that has to be clearly studied from the beginning of the project. Equipment located in ethics zone must be manufactured with specific characteristics, and they are more expensive. Also, the communication and control system was carefully designed and reviewed in order to make the plant as automatic as possible. This plant can be controlled and monitored in remote mode from Madrid. This is the control network drawing where all the communication units are represented. The construction phase was less than 4 weeks, 3 weeks for the civil works and connections with the biogas plant, and 1 week for the installation. The equipment came from Holland, pre-installed in a container and in 2 pretreatment skids. 3 trucks arrived at the farm, and the same day, the main equipment were located in their place. All the project from the beginning to the design, from the beginning of the design till the end of the operation was about 12 months. Let's see this video for the construction and commissioning. This is the main container for the equipment. This was the assembly. The skids outside, the pretreatment skids. The connections. This is the biogas pipe getting into the upgrading, the refueling station, the assembly, with the buffer tank, the bottles to fill the cars. These bottles are for 250 bars, the commissioning of the compressor, and this is the outdoors skills. A view of the plant inside the membranes, the gatekeeper, the pipes to distribute the biogas and biomethane, the compressor, the control room with the analyzers, the two analyzers, biogas and biomethane. This is the biogas with 65.9% in methane. And this is the biomethane with 96% in methane. The three filters. The SCADA system, the signal process. Here we were producing 100 cubic meters of methane, different days of operation. This is the pretreatment, SCADA, the compressor, and the membranes. The gatekeeper.
Carmen, please, we cannot see the slides. The slides, we cannot see them.
The video?
Yes, the video, yeah. It's not possible to watch it?
You didn't see the video?
No, they don't see the video.
Oof. Okay, sorry.
It's in the Metamorphosis project.
This?
But we cannot see later.
The video that you didn't see?
Yeah, we cannot watch it.
A ver, let me try again.
Karen, I think you shared only the PowerPoint. You have to share your entire screen, or you share the video. Unshare and share the video, yeah.
Share and the video also, but how can I do it?
I think at this point you have to unshare your screen, and then you share it again only with the video.
Okay.
Because I assume you don't want to share your entire screen.
Okay.
Yeah.
And now, you see?
Yes, we see.
Yes, it's okay.
Let me, sorry. You hear me?
Right, we are watching it.
Okay. This is the main container with the equipment inside.
Right.
The pretreatment skids, the filters, and the chiller and the blower. The connection works. Pipes and wires already mounted. Here are the dates of what is each work to be done. The pipes between the skids and the main container. The biomethane pipe to use to return to the digesters. This is a drain pit that is important in an upgrading plan for the biogas. This is the biogas inlet. Now is connected to the upgrading skid. This is the refueling station. The compressor, the buffer tank, and now we are going to see the bottles, the pressure bottles. These bottles are in 250 bars for feeding the cars. Inside is the biogas compressor. As you see, this is very compact. It's not a huge plant. It's easy to install and it's easy to operate. This is the gas refueling station inside the membranes. This is the pipes for the biogas and biomethane. And this is the compressor. That is the main machine. The control room with the PLC and the electrical board and the analyzers. These are the two analyzers for biogas and biomethane. This is biogas with 65.9% in methane. And this is biomethane with 96%. The skids of the filters, the SCADA system. We monitor this plant from Madrid. These are some days in operation. This is the pretreatment. If you push in the screen for the pretreatment, you get into each element. This is the compressor. And these are the membranes. And this is the final control to send the biomethane to the pipe. The THC dosing and the analyzers. This is for biogas, the 3 points to analyze biogas and biomethane. As you can see, the control is very complete. And this is the plan. Sorry. So now I will go back again, no? Okay, you see now the screen, no?
You can see it.
Okay. So this is the panoramic of the plant. From the left to the right, it can be seen the chiller for cooling the biogas, the blower, and the 3 filters that I showed you before, and behind the main container. Inside the 3 stages of the membrane. Stage 1 with 5 membranes in the middle part, stage 2 with 8 membranes in the lower part, and stage 3 with 6 membranes in the upper zone. As it can be seen, there is free space for increasing the number of membranes in case the biogas will have worse quality than expected in the design, or if we would like to increase slightly the biomethane production. This is the compressor that we have seen before. The biogas to be required pressure between 8 to 16 bar, and the compressor is a screw compressor made in Italy by Adicom, and it includes filters and cooling devices. The gas refueling station is also part of the project. It includes the compressor and the storage. This is the SCADA system that we have seen in the video. The upgrading plan is monitored continuously, but means this PLC. The control scheme can be seen the process starting from the digester to the left, following by the heat exchanger, the blower, the filters, and the compressors. In order to monitor the biogas and biomethane, the plant includes also 2 multi-analyzers. These analyzers take samples from different points from the process. The lower the methane concentration is in the biogas, the higher the required pressure in the discharge pressure. Finally, the biomethane coming from the membranes with over 95% in membrane is sent to the refueling station. In case the biomethane does not comply with the quality, it will go back to the digester. We don't throw to the atmosphere any methane. And finally, this is the project landfill, Elena landfill, that is already in construction. Here you can see the civil works that is already developing. The upgrading plant is for 350 cubic meters per hour, producing more than 180 cubic meters per hour of biomethane. The upgrading technology is also membranes, and the biomethane is going to be injected into the natural gas grid the following months. These are their movements. This is the container of the upgrading plant that is being transported to Barcelona, and these are the skids for the pretreatment. What is important to see from these photos is that this is very small. It seems like a biomethane plant is something complicated, but it's not very easy. So in conclusion from my presentation is that we consider biomethane a key energy in the decarbonization future of the world. It promotes the use of renewable energies, as solar or wind. When a renewable energy is produced but is not consumed, it cannot be stored easily. It can be used in producing biomethane and inject it into the natural gas grid. This is the easier way to storage energy. It contributes to the security of supply and energy independence. It improves the environmental management of any organic wastes, avoiding aquifer contamination, and generates synergies with agricultural and food industries. Helps to support rural development, job placement, and population in agricultural settings. Thank you very much. And if you have any question, I think
Yes.
it has been a very technical presentation, but if you have a question, I'm ready.
Thank you very much, Carmen. Very interesting intervention. So we have some questions. Let me go to the questions. The first one is, when you said the biomethane produce can power 1,000 cars per year, do you mean electric vehicles or just normal biomethane fuel vehicles?
Biomethane as natural gas.
Right. And also, what is the
electrical.
feasibility of having biomethane power charging stations for electric vehicles is considered?
Sorry, repeat.
What is the feasibility of having biomethane power charging stations for electric vehicles?
In gas stations, for biomethane can be used any refueling actual stations for gasoline. We mean you can install in any place an electrical device. The feasibility to install there, yes, you can do that. But the advantage of the biomethane is that you can use for any of the uses. But if you want to produce energy for electrical cars, maybe it's easier to produce biogas and produce with a cogeneration motor, produce electricity. This will be more feasibility.
Another question says that is a very interesting technology. And the question is, can you tell us about the efficiency of this technology and how much can the production of 1,000 kilograms of biogas cost? Is it a transposable technology from Guinea to Niger, for example?
From?
Is from two countries, Guinea and Niger in Africa. And the question is, Guinea and Niger. And the question is it a transposable technology?
Yes. Yes, I think so. In any place where the biogas, you can produce biogas from organic matter, you can install a biogas production and later the biomethane. Of course, in any place, or even just to produce with the biogas energy with a motor generation. So it's possible to install from the wastewater treatment plants or from the organic wastes sent to a landfill. You can get the biogas and produce biomethane.
Yes, another question is, how will take into consideration environmental and safety concerns for this technology?
This technology is it's completely included in the environmental protection because we are reusing the wastes, the organic wastes that if you leave them in the atmosphere, it will release the methane that is more that is contaminant, 25 times more contaminant than the CO2. So in any possibility to storage in a closed tank the organic matter and produce biogas in a controlled and closed system and produce biomethane, it's completely included in the protection. It's a renewable gas, it's green gas, so it's good for the environmental.
Right. And another question, what are the different steps when designing biogas production projects?
The first step is to identify the organic matter that you have available, to study with this organic matter how much biogas you can produce, and with the quantities and quality of the organic matter and the biogas, then you will ask for a biomethane production installation. I think the most important is the residual, the wastes that you are going to use to produce biogas. Identify the quantity, the quality, and then design the biogas plant. The main part of this is the biogas plant.
Another question, what are public health measures taken to ensure that the community, the environment, and the workers where the biogas and biomethane plants are located and are protected from respiratory complications?
Can you repeat, please?
Yes, it's a long question. What are the public health measures taken to ensure that the community, the environment, the workers,
okay,
yes, are protected from the respiratory complications?
The helps, you mean the economical helps?
The health.
Help,
The
economical,
health of
you mean
people.
public health.
Public health, yes.
Public health. In Spain, I mean, in Spain, there are some helps that depending on the area of Spain and depending on the organism that is requiring for the help, it will be graded or not. It depends. It depends. I don't know. In Africa, I don't know. I don't have any idea.
And what is the investment cost of this for this project?
In one of the, I think the presentation is going to send to everybody. In one of the slices, in the resume, I put the investment cost in each project. For example, in Ben's project, the investment was 1.1 million euros. It depends. It depends on the flow of the plant. If you want to know more or less how much does it cost an upgrading plant, I have there is a slice with a curve with the cost ratio for capex and opex in each one. For example, for 1,000 cubic meters per hour of biogas, the upgrading plant with a normal biogas, not with landfill biogas because it's more complicated. The cost could be around, let me see if it was 2 million or 1 million point. Let me see, for 1,000 cubic meters of biogas, the investment, the capex is around 2 million euros. And the opex, will be, the operating about 500, but this is with expenses, Spanish expenses. So, I mean, maybe in Africa, the electricity is cheaper. The main cost is the electricity consumed.
Only when you go.
Yes, another is how is the effluent from the process for reducing health risk, and this effluent have any use?
Could you repeat, please? Sorry.
Yes, I don't understand very well this question, but we leave this question for answering by the email.
Yeah, maybe it's easier by email.
Yeah, I think so. And are biogas and biomethane projects scalable after initial commissioning? Are there any probable technical constraints with regard scalability?
You mean to increase later the capacity of the plant, or just by if it's as easy that a small plant as a big plant? I think, for example, for a plant for 200 cubic meters per hour, that is the one of the video from Metamorphosis, there are just 3 trucks. But for example, if you want to install a plant for 1,000, in one container is not possible. So maybe instead of 3 trucks, maybe there are 6 trucks or 7 trucks. So it's more complicated, but not complicated at all. It's more quantity of containers that arrive to install.
Yeah. The last question is, let me see. Yeah, summarizing, because what are the environmental impact issues associated with biomethane project?
There is no an environmental effect because, well, yes, it's a positive environmental effect because, as I told you before, when collecting the wasted from a farm, for example, and put it in an hermetic tank in the digester to produce biogas, you avoid the possible contamination of the methane from the sludge getting into the atmosphere. So you avoid this. Besides, the animals wasted also has the problem that many places contaminates the aquifer, the water down the earth. So with this system, you avoid this problem because the digester collects the sludge. Besides, the off gas that you send to the atmosphere, because in the upgrading, in the biogas, you collect the sludge. You have them in a hermetic tank. You send to an upgrading plant where there is no leaks in methane. And then you separate the methane to the CO2. So you send to the atmosphere the CO2 with less than 1% in methane. Depending on the technology, on the upgrading technology, this leak, loss of methane could be even lower, 0.1%, for example, from chemical absorption. So the leak to the atmosphere of methane is much lesser than if you leave the rest of the animals in the ground.
Okay.
It's infinitely less.
Okay, we are running out of the time. We have another question, and it will be answered through the internet, through your emails. So I have to say that the presentations are already delivered by the trainers. Thank you very much. And you can find them at ECREEE webpage, and in AMENET webpage as well. AMENET is the network of universities, and the webpage of AMENET is www.amenet.eu. I repeat, www.amenet.eu. So thank you very much for your attention. Thank you very much for the trainers. I think your contributions were quite technical, but there are excellent contributions to this seminar, to this training. And tomorrow we keep having our lectures, and at the same time of today, right? So have a good day, everybody.
Okay, thank you, everybody. Thank you.
Thank you.
Thank you, sir.
Okay, tomorrow at the same time, the Thursday.
Right.
Thank you. Thank you. Thank you.
Don't forget, when join the training.
Thank you very much. Bye.
Bye, thank you.
Your full name.
Thank you for the presentation.
Country, so that it is easy for us to
Thank
access
you.
your participation. Please don't forget the